let's say this O. So an object travels from point A to point B, making an arc, the length of which is delta S. R is the radius of circle. So as we can see here, this arc makes an angle delta theta at the center. So we can say that the angular displacement of the object when it moves from point A to point B is delta theta. Now let's see what is the direction of angular displacement. The direction of angular displacement is going into the plane for clockwise rotation, and for anti-clockwise rotation it is coming out of the plane. The magnitude of angular displacement is given as delta S by R, where delta is the length of the arc and R is the radius of the circle. And in vector representation we can write delta theta, which is our angular displacement, as R cross delta S by R square. So let's explain this. So here we can see that we can write delta theta as delta S by R, where delta S is length of this arc and R is the radius. Also in vector representation we can write delta theta as R cross delta S by R square. Here the direction of radius vector is radially outwards, so this is our R vector, and direction of delta S is tangential to the arc. So if this is the arc, then the direction of delta S would be tangent to it, so it would be perpendicular to the radius vector. This is our delta S. And this angle is 90 degree. So we can see from here the direction of R cross delta S would be going into the plane for clockwise rotation, and for anti-clockwise rotation the direction of delta S will change. It will be here, and so the direction of delta theta would be coming out of the plane. Now we will define angular velocity. First we'll define average angular velocity. Average angular velocity is denoted by omega, and it is defined as delta theta by delta t, where delta theta is the total angular displacement and delta t is the total time of journey. Similarly, we can define instantaneous angular velocity, which is rate of change of angular displacement of an object. So omega will be limit of delta theta by delta t, where delta t tends to 0, or it is d theta by dt. Similarly, we can define angular acceleration. Angular acceleration is denoted by alpha, and average angular acceleration is defined as the change in angular velocity divided by the time interval during which the change has occurred. So alpha will be equal to delta omega by delta t, or it will be equal to omega 2 minus omega 1 by delta t, where omega 2 is the angular velocity at the end of time interval delta t. At the end of and omega 1 is the angular velocity at the beginning of time interval delta t. Now instantaneous angular acceleration will be rate of change of angular velocity with the time. So instantaneous angular acceleration alpha can be written as d omega by dt. We have already seen various equations of motions in one dimension. We have their counterparts in angular form also. So what we need to do is we can replace the various one-dimensional quantity like final velocity v, initial velocity u, acceleration a, and displacement s with their angular form counterparts. So v can be represented as omega f, which is final angular velocity. U can be replaced with omega I, which is initial angular velocity, A can be replaced with alpha, which is angular acceleration, and S can be replaced with theta, which is angular displacement. So we have this equation. Like if you remember, the counterpart of this equation in the one dimension form would be V is equal to U plus AT. Similarly, this is nothing but S is equal to UT plus half AT square. Similarly, we have three other equations. So these are almost similar to the equation that we have already seen in motion of one dimension. Now we'll see the relationship between tangential and angular velocity. Tangential velocity is defined as delta S by delta t, where delta S is the length of the arc and delta t is the time interval. So suppose an object is traveling in a circular path and it travels a distance of delta S in time delta t. So we can define tangential velocity, that is V, as delta S by delta t. Now we have already seen that angular velocity omega can be defined as delta theta by delta t, and delta theta is nothing but angular displacement, which is defined as delta S by r. So here we have omega is equal to V by r, or V is equal to r omega. So this is the relationship between tangential velocity and angular velocity. The vector form of the equation for tangential velocity can be written as V is equal to omega cross r, where r is the radius vector. So as we have already seen that the direction of omega will be coming out of the plane for anti-clockwise rotation, and for clockwise rotation it is going inside the plane. So we'll denote the direction which is coming out of the plane as this, and the direction which is going into the plane will denote it by this figure. So suppose at this point the object is moving in anti-clockwise direction, so the direction of omega would be this, and the direction of radius vector r would be radially outwards. So the direction of tangential velocity v would be perpendicular to both omega and r.